postgraduate studies at the University of Illinois in USA. And then worked with Ford Motor Corporation for many years before joining again the engineering faculty. And these 2 years he is with SLIIT on his sabbatical leave. And he is ready. I will invite him to start the talk. And he has been working with the dam safety unit of Nihal Authority for a long time. So we will hear about the Victoria Dam and its monitoring system today.
Thank you for the kind introduction. What I'm going to present here is the result of work done by many people over many years. So what I propose to do is to give you the highlights of their work. I also have had the privilege of working with these people. Most of them were my students, undergraduate students and graduate students. I will give the credit to some of them during this presentation and later. I have separated this presentation into 2 parts. Now, this is my attempt at a little bit of intrigue, saying, okay, deciphering movements, Victoria. I have divided this into 2 parts. So, part 1 is about how Victoria moves. Now, before your imagination runs right, this is what I'm talking about. This is the Victoria I'm talking about. Okay, the Victoria Dam, which is the largest concrete structure in the country. And we have observed certain deformations, movements of this dam. This is now 30 years old, but that is very young as far as dams go. And during this 30 years, we have observed certain deformation patterns that are a little bit unexpected, to say the least. So, what I would do is, in the first part, I will show you what we have seen about how this dam deforms and how those deformation patterns have changed over the years, and we will see why they are considered unexpected deformations. In the part 2, I will briefly tell you how our research programs have looked at this particular issue and tried to understand what is going on. Okay, so that is the 2 parts. These are some views of the Victoria when it was spinning, and this is a calm time, and this is when you see it from upstream, and this is what you see from downstream. Okay, so in our discussions we will be talking about a few important parts of this dam. Here you see the openings that are there for the water to spill out if the water level tries to go above what is considered safe. Inside this there are what we call spill gates, and at the bottom you have what we call the bottom outlet through which you can discharge water if necessary. If you can observe the structure, the dam itself has 2 planes of curvature. The dam curves in this plane and it curves this way also. If we go back to this view you can see the curvature much better. Here it is curving. If you look at it in plan, it will curve. In the vertical direction also it curves. So this is called a doubly curved arch dam. Arch is, you know, when you have something curved. If you take a beam and if you curve it, then you have an arch. So this is arches going in both directions. So this is called a doubly curved arch dam. And some facts about the dam. Height 122 meters from the bottom of the foundations to the top of the dam. It is 122 meters. Length along the crest is 520 meters. That is just to give you some idea about the size, magnitude of the dam that we are talking about. Its economic importance to the country is given here. It has a generation capacity of 210 megawatts. What is more important is the energy output, 500 gigawatt hours per year. Now, if you translate that into monetary terms, at your home, you will be paying up to a maximum 45 rupees per kilowatt hour, what we call a unit, from something like maybe 10 to 45 it varies. So if you say average is 25 rupees per kilowatt hour, 1 gigawatt hour will be 1 million kilowatt hours. That is 1 million units. So here we are talking about the production of 500 million units of electricity, and 1 unit is 25 rupees. So you can do the calculations. That is the economic value of this dam. It provides 6% of the country's energy demand. So this is a very important structure. Even just if you consider the power generation alone, it becomes a very important structure. But it is not only for power generation, it has other purposes also. Therefore, this is part of this multi-purpose Mahaveli scheme. So, this is, needless to say, a very important structure. That is why we are interested in the health of this structure. Every little movement that it makes, we want to know what is going on. How do we know about the movements of this dam? If you look at the cross section of the dam at the center, now this is our 120 meter height, 122 meters from here to there. And at different points in this dam, there are vertical holes. Well, I shouldn't say holes, they are vertical cylindrical voids, through which we have hung pendulums. A simple thing, you hang a wire from the top, have a weight at the bottom, in a simple sense. You hang it from there and let it hang. You connect it to the top and hang it like that. And now, when the water is there, when the water pressure comes, this dam will move to the right. It will slowly bend a little bit. And when it is bending, this point will move to the right. So the pendulum line also will move. And then we have measuring instruments inside at different levels. We can see how much it moves. So that is one way of measuring the deformation that occurs in the dam. Inside the dam, and these little places that you are showing, these are what we call tunnels. Inside the body of the dam, it looks like solid concrete, but inside you have these tunnels, horizontal tunnels that are going from one end of the dam to the other end. And at different locations in the dam, you have this pendulum that allows you to measure by how much the dam is going to move. That is not the only way we measure, but that is one of the ways in which we measure the movement of the dam. If you look at the plan view, this is the 520 meter length. And one other way of measuring the movement of this dam is to, we have on the surface of the dam, now this is the plan view, so the dam comes up here. On the surface of the dam, we have certain markers embedded in the concrete. And then from the sides, there are serving stations. Two here, one there, another one here, another one there. 4 serving stations. We go to each of those stations and find the angle to that mark from the 4 serving stations, and then you can calculate the horizontal position of this particular point with respect to these 4 stations. And there are a large number of such what we call targets on the surface of the dam. So that is another way we can measure the small movements of this dam with time, and it goes up and down with the water level and so on. So these are the 2 main ways in which we measure the movements of the dam. Those are the movements that we are going to talk about. This is just some numbers. We don't have to worry too much about that. Let's skip that quickly. This is a fairly well instrumented dam. There are many instruments in the dam that allow us to keep track of what is going on. To measure the dam deflections, we have the 7 normal pendulum. That is the one I mentioned earlier. You hand pendulums from different points in the dam. And then 24 precise leveling studs on the crest. Now this is the crest of the dam. So along the crest of the dam, we have leveling studs. And we can use precise leveling to find the levels of those studs along the crest of the dam. And then 48 survey targets on downstream face. So the downstream face here, we have those survey targets that I mentioned earlier. You measure the angles to those targets from the surveying stations. We can find what is happening at each of those 48 points. That is not all. There are some other types of instrumentation also. We will not worry too much about it, but it's sufficient to say that inside the concrete we have about 300 strain gauges that measure the strain at certain selected points in the dam. Then there are about 60 thermometers that will measure the temperature. Of them, some are not functioning now. These within parentheses, we have given the number of those that are not functioning. This is not bad. After 30 years, out of these 300 strain gauges, only about 50 are not functioning, so 250 are functioning. That's pretty good. And same here. Then there are other things that is of no concern to us as far as this particular presentation is concerned. However, whatever instrument you have to measure, there's nothing that can substitute human observation. So this is just a snap to show you that the engineers in these places still go manually on the side of the dam even and observe some of the features that are of interest. Okay, so we have to be thankful that there are people who are dedicated to their work, who are willing to do this sort of thing also. Now, if we come to the leveling stud that I mentioned earlier. Now, we have marked with this yellow dots the locations, approximate locations of those leveling studs. So, you know how to do leveling, of course. So, you start from somewhere here. There is a fixed benchmark, and from there you come with precise levels, not the kind of levels that we are using. These precise levels can be up to 1/100 of a millimeter done every year. Once when the water level is low and once when the water level is high. So what we have seen is something like this. If you look at it from the left end, sorry, this is the left bank and the right bank. If you look at the levels of those stars, with time, this is 1986, this is 2009, these levels have been going up. At every start we have observed that. But don't worry too much, because the values are, we are talking about 50 millimeters in the center, and the most recent survey we found that at the center it was about close to 70 millimeters. This one is close to 60, that was 2009. But still, it is a fact that the crest of the dam is slowly moving up, heaving up. This is not something that we thought we would see. Okay, so that is one of the concerns that we have. This one gives the 2014 value also last year. Some of our students went and with them, the engineers at Victoria, they measured the elevation along the dam. Now you see it has gone up to about 70 millimeters at the center. So if you put it in some perspective, this is what has happened over the past 30 years. If you just draw these displacements along the dam, this is what you will more or less see. At the two ends it is not moving, but as you come to the center, things are moving up, and the maximum we had is about 70 millimeters at the center of the dam. The other way we look at the dam is by looking at those survey targets. Remember, I told you that on the downstream face of the dam, we have all these at these different locations. We have put little markers, and then from the 4 survey stations on the downstream, the bands, you measure the angles, and then you can decide what is the movement of each of these little dots on the surface of the dam. So when you look at these movements, what we would normally expect to see is this. Now this is our dam in plan, and this is the upstream. So when the reservoir gets full, there is pressure on the dam from the upstream side. Therefore, the dam will move in a little bit. All these points will move in a little bit due to the deformation that will result from the compression that will occur in the dam. And when the water level is low, it will come back a little bit. But we would expect it to move downstream when the water level increases. Over the years, this also has changed. The way it moves when the water level goes up has changed. In 1984, this is what was observed. Now this yellow line is the undeformed configuration. Now you might wonder why, when the dam is a very smooth curve, why do we have this yellow line going like that, not that smooth? That is because the markers that we are looking at are not at the same that we get from the pendulums. There are 7 pendulums. The tallest one is right here. Others are on the sides. if you look at one of those pendulums and there are readings, this is what you observe. Once again, in year 1985, the displacements were like this, but by the time you come to 2011, the displacements have moved upstream. Same here, low order level, high order level. Everywhere this is happening, consistent. We expect it to go downstream, but what we see now is that it is moving upstream. So don't worry about this. What do these observations tell us? Many people who looked at this, they think that this has indicated that certain permanent deformations have taken place in the dam. That is why it is moving upstream when we think it should be moving downstream. That is why the crest is heaving up when we thought that the crest would stay level. So all these are indications of certain permanent deformations that seem to be taking place in the dam, and we want to know why. We ask questions. We ask, why is this happening? Now this is just the trend. If you, these are the months since impounding, months since filling the reservoir. You can see that this trend line continues and there is no sign of any leveling off. It continues to change. In fact, it seems that it is increasing its rate. That is why, if it was leveling off at some value, we can say, well, after some time it will be okay to level off and come to some stable position. I'm not trying to alarm you. There is no possibility of impending big failure of the dam. But these are signs that we should not neglect. Same. So, what is concluded by the people who observe these changes is that the difference between 1985 movement and the current movement is the permanent deformation that has taken place in the dam. This yellow line is the irreversible deformation. If it was elastic, then when you push, it will go there. When you take the load out, it will come back to where it was. But now, you see that there are permanent deformations, irreversible deformations that are taking place. And that is where we start asking questions, because these are things that we did not expect to happen. So, this is the picture that leaves us with many questions. Okay, so that is the part one, for which I had nothing to do. Basically, this is what has been observed by the engineers at the Victoria site, who have been carefully monitoring the dam. Here I must say that credit must be given to engineer Hasant Kodagam. He was with the Victoria Dam for some time. Now he has left Mahavali Authority and he is in CSEB. And also the chief engineer who was at Victoria, Rohan Arup, engineer Rohan Arup. He is now the project director of the dam safety program. These two deserve a lot of credit for this information that I have presented. Okay, so before I go to part 2, if you have any questions about these observations, of course we have questions about this observation, but if you have any questions about what I have said so far, please feel free to ask them now, or we can take questions later. I hope you have some idea of the problem that we are looking at. Still we haven't told you what we are doing, but this is the situation that requires our attention.
I have a small question. Now, over the 80 years, some of these measuring equipment, yeah, precision of measuring certain things have increased. So probably in 1935, so if someone measured something as 10 millimeters, today we can measure it very accurately. That also comes a little bit sound.
Yes, the increase in the level of precision that we can achieve in our measurement, is it capable of explaining this? And in any case, there hasn't been much of an improvement in the precision of the measurements that they are taking. They are very, very basic measurements, as you can see. The crest leveling, precise leveling that has been there for past so many years, they are still doing the same thing. You know, you look through your telescopic sight and then do the leveling. And there are 70 millimeters there. Even if I did that, I don't think I can get 70 millimeters error or something. So it is real. And these are agreeing with each other, like the measurements that we see on the pendulum. Now, pendulum measurements are also very simple. You have a wire that is going down, and then you have a ruler here, well, with a micrometer, basically a vernier. And you measure by how much the wire is moving. So there isn't any major improvement in that also. And they are agreeing. What we see from the pendulum and what we see from the targets on the downstream phase, they are telling us the same story. So Victoria is sending us some message through her movements, sending us a message, and we need to understand the message if we are to take good care of her. Okay.
Special reference to some reference?
No, the reference will be the 4 stations on the downstream side, far away from the dam. The 4 survey stations.
What about them?
Every few years, they get the surveying department to take from farther points and come to measure those survey stations. So they have not seen any major, substantial or significant movement of the surveying stations. So otherwise, yes. But once again, all these are giving us the same story. And they are independent measurements from using the pendulum and using the phase targets and using precise leveling. All are giving us the same similar messages. And not only that, I did not go into the details. There's a whole wealth of information here which we have not even touched. The strain gauge readings. We have 300, 250 or strain gauges that are still working. And those readings are also telling us the same story. So this particular movement of the dam, I think, is real. Maybe the value might be different by a couple of %, but not more than that.
But the range of maximum around 7 centimeters.
Yeah, that is the crest heaving. It's continuing to go up. At the center, about 70 millimeters. Now remember, this is 520 meter long path, but we can't ignore.
Are those deformations are creating stresses and strains on the dam?
Of course.
The measurements are justifying those.
When we come to the next part, we will come to that. But what you are asking is the right kind of questions. And we have more questions than we can answer. So some of you want to try to answer some of those questions, the opportunity is there. We have a lot of information, we have to go through them, orderly, clarify them, and then start answering questions one at a time so that we can understand what is going on here. This is unfinished business, so I don't have at the end of this presentation, I don't have an answer. All I will do is I will tell you what we have been doing over the past few years. But there's much more to be done. So if you are sort of comfortable about the idea of movements in the dam and the idea that there is something going on that we do not understand, I would like to move on to this part 2. Actually, this part 2 is where we came in. When we saw the part 1, we thought that there are some questions that need to be answered. So now once again, what I'm going to show you is the result of a large number of people who are working at different times over the past maybe 10 years, looking at different aspects of this problem. Almost all of them were either my undergraduate students or graduate students, and a lot of them were undergraduate students. So with undergraduate projects, you know, there is only very limited time, 3 months, 6 months, and you can't get much done. But this is the combined result of a large number of such groups working patiently over little parts of this big problem. So I'm very grateful to them, and I owe a bit of gratitude to them. I will give some credit to them later. I will list some of their publications. So earlier was the message that Victoria is sending us, and now we are trying to understand this message. We still don't understand it properly. That is what we are trying to do. Okay? Now here we come across this idea of what we call alkali aggregate reaction. Many experts who looked at these deformation patterns have come up with the same idea that maybe a phenomenon called alkali aggregate reaction that is known to occur in concrete might be responsible for this observation that we have seen at the Victoria Dam. So the consultants to the Victoria project, Alexander Gibbs and partners, now they are both Jacob Gibbs and so on, they also have the same idea. Okay, so here is where we start our work. We start with the observation that over the past 30 years, when we started it was past 20 years, Victoria is bulging upstream on one hand and heaving upwards along the crest. So the consultants, Alexander Gibb was the designer, then they merged with another company, they became Jacob Gibb, and they also looked at this in 2003, and they thought that, well, of course they concluded that there is a progressive expansion in the concrete, but they said they do not see any signs of distress. That is, as a result of this expansion, at that time they had not seen any adverse effects, any signs of adverse effects on the dam. But they thought we should pay attention, monitor the dam, and conduct some studies. And they suggested that maybe we can use finite element techniques to simulate what might happen in the dam in future. So we asked some questions. These are the research needs that we thought was there at the time. Why does Victoria appear to expand? Why? That is the main question. This is doing something that we did not expect. Why is she doing this? Is Victoria suffering from EAR? As some people have suggested, including Alexander Gill. We want to know, is this true? Is alkali aggregate reaction responsible for this in Victoria? So, I think this projector has this color problem, right? You can't read this. I can't read that either, so I will read it from here. What I have written there is what is required is detection. Is Victoria suffering from AR? We need to be able to detect the existence of AR. Now that can be through either experimental methods or analytical or numerical methods. If we can answer that question, we ask another set of questions. What might happen to her in future? So far, what we have seen is this, but what is going to happen in the future? Are we in trouble? Is there going to be some problems in time to come? So those are legitimate questions for us to ask. And that also requires, in red, what you can't read there is